I can write too.
Paragraph material.
Oh, yeah, I did.
You do it yourself again?
Yeah,
Nice.
I apparently knew that. 1, 2. I think it's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's homework. 1, 2.
Yeah.
New desk setup, because we're doing something crazy in class. And
What are we doing? We know yet? Or
What?
secret?
No, yeah, I mean, it's not that crazy. You'll just get in groups and like learn one topic good enough to teach
Oh, okay.
the rest of the class. All right. This everyone probably. All right, so remember last time you were here, we finished 10-1 all the way through. We even did something I wasn't planning on, which is telescoping series. Remember that won't be on the AP test, but they're kind of neat anyway. But what will be on the AP test is this integral test right here, which is now mine's all messed up because I messed with my formatting. But this is on a different page for you guys. But the integral and P series test, that's what this section's all about. Did I start recording? Yes, I did. Okay. So the integral test says, here's the short version. If you're curious about if a sum converges or diverges, then you could treat this like a function and take the integral from 1 to infinity, or from wherever the lower bound is to infinity, and that will sorry, if that converges, then if the integral converges, then the sum converges, and vice versa, actually. I think that's all I have to say about that. Then you'll see an example of what I'm talking about. Oh, no, there is one more thing to say about that. In fact, I've seen this on an actual AP test where they ask you this directly. So hopefully that would be 3 points. If you can remember this, that the integral test only applies if the function at play is continuous, positive, and decreasing. Those 3 conditions have to be met. And then you can apply the integral test, but most of the time that's like automatic. So a lot of times you don't have to worry about it. But like I said, on the AP test, I saw it ask directly what are the 3 conditions. So those are the 3. All right, examples. Watch this. This is going to be a good review of how much you remember about infinite integrals, the improper integrals. So it says determine whether the following series converge or diverge. Right now, you guys at this point in the packet only know one way of checking, and it's checking whether this is geometric or not. But in this case, it's not geometric. Geometric ones are the ones that look like number times ratio to the nth power, and that's not what this looks like. So the only other thing you know is the nth term test. So maybe to remind you of what we did last Friday, when we do the nth term test, not a requirement, but just a good reminder. The nth term test says if I take the limit as n goes to infinity of these terms, if I don't get 0, then for sure it will converge. But in this case, I mean, you can kind of just do this in your head. Do you guys know that limit real quick? Okay, all right, good. Yeah, the bottom of this gets enormous. The top stays at 1, so 1 over huge is will tend towards 0. Nice. Okay, so if you don't remember well, then the nth term test does not say that this limit being 0 means that this will converge. It just says that it has a chance of converging, but we don't know for sure. So that's why these tests are good for when this is not geometric, so I don't know if it's going to converge or not. And then I tried the nth term test and I got that it could possibly converge or possibly diverge. That's when you can use this integral test to like make sure that it does converge or doesn't. Cool. Okay, so integral test. Remember, I have to check whether I can even use it by checking if 1 over 3x plus 4. I'm treating this like a whole function now. whether that's continuous, positive, and decreasing are the three conditions. So first of all, if I plug in numbers from 1 to infinity, is that gonna be, well, let's just do the easy ones. For sure, that'll be positive. Decreasing, that is what it sounds like. Like the bigger number I plug in, does this get smaller and smaller? Yeah, okay, so decreasing, yes. And then when I ask about continuous, I just mean in the interval from 1 to infinity. So is that the case here? Yeah, that's continuous everywhere above 1 for sure. The only place where it's not, let me just check that you guys are looking in the right places. Where is this not continuous? Yeah, wherever the bottom is 0, that's when you should be worried. But that's going to be at negative 4/3. Like if you have enough foresight and can solve this in your brain, that would be at negative 4/3. That is not in the interval from 1 to infinity, so you don't got to worry about that. Everywhere else, you can plug in a number and not get 1/0. So that's why I'm saying yes, it's continuous where it counts. Cool. Okay, so that's just me like covering my bases, making sure I will like check the requirements. Then here's us actually doing the integral test, which just says take the integral of give me a sec. It didn't move any of these. That means I was in the table the whole time. All the borders, give myself some room. Okay, erase this, erase this. All right, now. So saying the integral test just says take this integral, and if the integral converges, then so does the sum and vice versa. Okay. But it's been like months and months since you guys saw an improper integral. So do you guys remember anything about improper integrals? Like what I would do next to take this integral? You remember?
You take the limit as a approaches infinity and then make a infinity.
Yeah, nice. Yes, exactly. Good job. Yeah. So these should not be like, oh, shoot, a new type of integral. Really, the only thing that in your brain, you're still thinking, take the antiderivative, plug in infinity, and plug in 1 and see what the answer is. It's the exact same thing as any other integral. But on paper, you remember how I showed you they get mad if you plug in infinity? Like you can't be doing math on infinity. So on paper, what you write is I'm going to take the integral not to infinity, but to this finite number, a, and then see what happens as a goes to infinity. It's a very subtle difference between first step and second step, but it's what you're supposed to do. Cool. Okay, and then now we take antiderivative and plug in a, plug in 1, and take the limit, etc. If I don't tell you the antiderivative, would you be, here's 10 seconds, nobody say anything. See if you know the antiderivative of that or would be able to get it. Okay, what'd you say? Anyone confident? Okay. All right, you should have said it's a natural log of this. Because this is linear, this is a skippable U substitution, but I've learned that most people don't like to skip it. So let me show the actual U substitution. U would be 3x plus 4, then du is 3dx. That's why I'm saying it's skippable, because if you just remember to divide by that 3, then everything is easy, and you get like that integral turns into this integral, or du times 1/3. And so the antiderivative turns into, well, will be a natural log of u, which is 3x plus 4, times the 1/3 from the du. So if you just said natural log, then you're close, but no cigar. don't forget to divide by the extra 3 in front of that. Okay, if this was 3x squared plus 4, then you can't do that anymore. Again, this is only for linear functions on the bottom. 3x squared plus 4 would be like probably an arctangent type of antiderivative. But okay, anyway, there's this, and I'm evaluating this at a and at 1, and I'm taking the limit as a goes to infinity. Okay, let me make this like its own side word. Okay, and then my next step will look like this. Limit as a goes to infinity of 1/3 times natural log of 3a plus 4 minus 1/3 times natural log of 3 times 1 plus 4. Okay, and then the second part is just 1/3 times the natural log of 7. But do you guys know where this is gonna head? I would be kind of impressed, but it's not super obvious. But if you think of the natural log graph and you think of what happens to that as it gets as x gets huge. Nice, yes, good job. Yeah, it goes to infinity slowly, but it does go to infinity. Here's natural log of x. So all I care about is what happens as I put in bigger and bigger and bigger and bigger inputs. Well, you can see it goes to infinity very, very slowly, but it grows without that. So the bigger number you plug into natural log, the bigger your output will be. So this will go to infinity. It doesn't matter that I'm dividing it by 3. A huge number divided by 3 is still going to be huge. Question.
Is there like a trick to knowing that they'll go to infinity, or you can just like memorize that?
I find no, I don't know. Like my trick is knowing my parent function, and that's it. Yeah, I don't know any tricks, but maybe somebody on the internet does. All right, so infinity minus a finite number, so this will equal infinity. And now I can answer the question, does the sum converge or diverge? You guys tell me. Just to make sure you remember the meaning of the word. Okay, all right, good, okay, I'm getting worried. Yes, since the integral diverged, and then it went to infinity, the sum will also diverge. So, maybe final answer here in red will be this sum from n equals 1 to infinity. 1/3 n plus 4 diverge. Cool. All right, that's the integral test. Is you just take the integral, see what that result is, and then the sum will share that result too. This had converged, then the sum would have also converged. All right, let me make some room for myself here on this one. Okay. And then we'll do the same thing on this. Again, the nth term test is a good like first thing to do every time, but you can usually do that in your head. If I take the limit of this to infinity, you can see that that would go to 0. So this has a chance of converging, but I don't know. Now let me check that I can do the integral test real quick. What was one of the 3 requirements?
Positive.
Okay. Okay, is this function always positive between 1 and infinity? Yeah, of course. Then what was the other ones?
Decreasing.
Okay, decreasing and continuous. Good job. The decreasing. Yeah, basically, if there's an n on the bottom, this is oversimplified. But if there's an n on the bottom but not on the top, then for sure it's going to decrease. The bigger and bigger number you plug into n, the smaller and smaller the output is going to be. So for sure decreasing, and then continuous, same thing. This will be not continuous at 0 because then I get 1/0. For everywhere else, I get a number, like a defined number. So continuous where it counts from 1 to infinity. Cool. Okay. So then the integral test applies. Oh shoot, I made that an n. But traditionally you make that an x. The The integral test applies, so you take this integral. Here's maybe, you want to try this one yourselves? I think you should. Okay, if you need guidance or reassurance, it's on the board, or at least a couple steps, sorry. Okay, if you need more reassurance, there it is on the board. Hopefully you did not say, although like I'm sure it may have happened to a couple of you guys that you said that this antiderivative was natural log of x cubed. But again, no, that does not apply. That has to be 1 over x, or at worst 1 over like linear function of x. But 1 over x to the power no longer applies. Natural log does not work. So you should have rewritten this as x to the negative third. And then the antiderivative is add 1 and divide by the new power. So x to the negative 2 over negative 2. If you rearrange this just so it's easier to take the limit, that would be negative 1 over 2x squared. And you plug in your a, you plug in your 1, and you take the limit. So that would be the limit as a goes to infinity of 1 over 2a squared plus 1 over 2. And then here I'm waiting to see how much you guys remember about limits. What would be the limit of the a part? Okay, good. Yeah, you should just be able to look at this and say the top is staying put, the bottom is getting huge. That means 1 over huge is 0. So this would be 0 plus 1/2. So 1/2. Okay, and then that tells you that since the integral converged, like you got a finite number out of this, then the sum also converges. So final answer would be that the sum from k equals, oh, I didn't even notice that there's a typo on here, but this says k equals 1 and this is an n, so both of those should be the same letter. Let me change this to an n. N equals 1 to 1 over n cubed. Converges. Okay.
Add 1/2 or no?
No, good job asking that. Yeah, easy, like quick little thing to like an easy misconception to have is that since the integral was equal to 1/2, that the sum equals 1/2. That is not true. Actually, that's what this next thing is about. This next little box, which I think is on the next page for you guys. Yeah, the next page says that this sum converges, but we don't know to what. But this 1/2, whatever the integral result is, will help you figure out like between what two numbers the actual sum will converge to. Okay, so join me on that next page. What time is it? 27? Okay, we have a lot of time. This is good news. So, okay, here's what I was saying, that the integral test bounds right here, tell you that the sum, the actual value of the sum, when you add it all together, will be between the integral, result that you just got and the first term plus the integral term that you just got. I'm letting you like catch that and understand that real quick. And if you're just saying, okay, sounds good, but you have no idea where this comes from, it's kind of fun to think about yourself. Yeah, I don't know if I should give you a hint or not, but if you're interested, come see me 1v1. One small hint is that it's a good idea to maybe draw a picture and think about what if this is the actual integral, is the whole area under the curve, think about what the sum would look like. And then see if you can get this bound and then this bound using that picture. You guys can do it, and every year somebody does come up with it. But if you have no idea what I'm talking about, then come see me 1v1 because it's kind of fun to talk about why this is the way it is. In fact, at the end of class, we can all think about it, but I don't want to run out of time. But again, if you're trying to think as we work, think about making a picture of the areas that the sum and the integrals would represent. All right, cool. And then this maximum error will be relevant in a little bit, but let's talk about the error bounds for, or sorry, the like upper and lower bounds for the sum first, and then we'll talk about an error bound and what that even means. So watch this. It says find an upper and lower bound for this series, which is the one we just worked on. So according to the box up there, a lower bound for the series would be the integral that we just took. And then an upper bound for the series would be the first term of this plus the integral that we just took. Okay, so the first term of this, what I mean by that is if I plug in the first number that it tells me to, that's the first term. So if I do that, let me show my work very explicitly. That would be 1 over 1 cubed plus that. Okay, and then good news is we already did these integrals, so this is a very short problem. The integral that we got here was 1/2, was it? Okay, so then 1/2 is the lower bound. Well, and then 1 plus 1/2. Let me do one thing at a time. Let me write this all. Lower bound is 1/2. Upper bound is 1 plus 1/2. In other words, this sum will be between 1/2 and 3/2 if I did add it all together. Boom. Cool. Okay. I think we'll have time at the end to talk about where these bounds come from. So remind me if I say lesson over without talking about where those come from, remind me that lesson's not over. And then example 3 says, approximate that the sum for that convergent series using 6 terms, include an estimate for the maximum error for your approximation. Okay, so what that means is instead of adding this to infinity, just add it to 6 terms. And then see how far off that is from your, like how far off that could possibly be from your actual answer. So we call those usually partial sums. You use an S of whatever. In this case, S of 6 for the 6 terms that I'll be plugging in. Okay, here's us getting that. That would be 1 over, first term would be 1 into there. So 1 to the 4th plus 1 over 2 to the 4th plus 1 over 3 to the 4th, 4, 5, and 6. Okay. And then I did already calculate this. This would be, just so we're all clear, that would be 1/1 plus 1/16 plus 1/81 plus the rest of them. And that would equal, if you calculated it, 1.08112. 1.08112. Okay, cool. So that's the sum up to 6 terms. But how far off is this from if I had gone to an infinite number of terms? That's what this second part of the box is about. And I'm pretty sure this comes from the same place, like from these bounds. So the farthest off this can be is, look at, if you use n terms to approximate the sum, then this will be at most from that to infinity, the integral from that to infinity of that function. So in this case, we use 6 terms to approximate the sum, so the maximum error would be what was my function? 1/4. Notice I went from 6 to infinity. Whatever I get out of this integral, that'll be the maximum error of that. Like, that's how far off I could possibly be. Okay, so let us calculate this real fast. Six to a 1/x⁴ dx. This is very similar to the one we just did, so let me do it real fast. Again, you're not allowed to say natural log of x⁴, x to a power does not, no longer applies. So you rewrite it as x⁴, you add 1 to the power and divide by the new power at a and at 6. It will give you limit is a goes to infinity of -1/3x³ at a and 6. Okay, and you plug in all your numbers. Of course, this goes to 0 again. Like the 1/a part will go to 0. The bottom gets huge, but the top doesn't. And then this part is like 648, I think, if you calculate it. Yeah, 648. Which is, if you want the decimal for that, which makes it a little bit more interesting, it's 0.015. Okay. So very, very interesting. Look at, we use 6 terms to approximate this infinite sum of infinite number of terms, and we got 1.08 whatever. And then did you catch what this 0.015 means? Like, what's that tell you? Got like the range error. Yeah, exactly. Is that the most this could ever be off in either direction? It's either this much more or this much less at most is the actual infinite sum. Which gives you kind of an idea of how far or how these sums work and why they converge. Is because it's the first terms that are adding the most values, and then after a little while, you're only adding little tiny decimals. That's why they have a chance of converging. So kind of interesting, and we only did 6 terms instead of infinite, and we were only this far off. This one is 648 off. Question and then question.
So if you did like 20 terms, it'd be like a really like even smaller number on the bottom, so you just be more accurate.
Yeah, exactly. If you went 20 terms, this would be very, very probably like 0.00000 many 0. Question.
Why is it only like an approximation of the maximum error and not like the actual like objective error?
Well, if we could calculate the error that easily, then we would be able to calculate the sum very, very just on this plus whatever. So usually these bounds are like an easy like a surefire, easy approximation of how far off they could be. Rather than like the actual errors, that would be probably a lot more. Nice. Yeah, these are good questions. All right, let's talk about P series fast as lightning because I want to talk about the Riemann sums or like where these bounds come from. I guess I just gave it away a bit, but P series, these are on a new page for you guys. But P series are, I used to get or every year I have to orient myself about which ones are P series and which ones are geometric series. Well, now I'm decent at it. But yeah, P series may confuse you because they look a lot like geometric series. Geometric series are here in red. They look like A times R to the N. And P series look very similar, but do you see the difference between geometric and P series?
It's like end of the R, it's like above the end.
Yeah, exactly. It's like now the N, the thing that you're increasing each time, is the bottom of the fraction where the power is staying put. It's staying the same. So geometric is like the backwards version of that. The ratio is staying put, but the power is getting bigger. P series are the opposite. Power staying put, but the ratio, the fraction is changing. So anyway, there you go. That's what's called a P series. And basically these work the way you would expect. Like if P is big, then you're getting really tiny fractions. Again, take 1/2 to the third, and that's really 1/8. That gets smaller. So the bigger P is, the higher the chance it has to converge, but then the smaller the terms get. So the quick summary of this is that they converge if P is big. They diverge if P is small, so between 0 and 1. And then you guys saw a sneak preview of this. If P is exactly 1, where is it? If P is exactly 1 right here, I'm reading this line right here that I'm circling with my mouse. If P is exactly 1, then that's called the harmonic series, which I've talked to you guys about for a couple times. It's come up already. So this would be the series 1 plus 1/2 plus 1/3 plus 1/4, etc. Which to the untrained eye, like in your gut, you feel like this should converge, but it does not. It doesn't get small fast enough. So that's harmonic series. This guy right here actually diverges. And that's another really interesting thing to like see why. But I don't know that we'll have time today. All right, but let's do these two quick examples that you guys have more in your homework. And then I want to talk about where those bounds came from. Okay, so determine whether the things converge or diverge. This does not look like a P series, but of course you can make it look like one. Okay, pretend that's all in one line. You can make it look like one by making that a 1/3. And then let me make sure I taught you good. Is that going to converge or diverge based on the fact that P is 1/3?
Diverge.
Okay. Whereas this one, you don't even have to rewrite. What's that one gonna do? Okay. Because P is bigger than 1.
How?
Big conversion. All right, cool. All right, 4 minutes. It's worth it. It's worth it. Let's go back and talk about these bounds. You haven't had much time to think, but did you catch an intuition on where these bounds came from? I would be like very, very impressed. You would have to take some time to think about it. But with 5 minutes left, I think it's just better to, oh yeah?
So just like you take the first one and then everything else that's never gonna be timed onto it, which is like the integral part, you just tacked on.
Yeah, that might be the intuition behind it. But they're like picture wise, there's a very easy way to see that this area will actually be bigger than that sum, which could also represent an area. The idea is, watch this. Which one should I do first? Here's the actual area. Let's say this is from 1 to infinity. So I'm looking at this area in red. This is the integral, I hope you agree. That's the value of the integral, that red section. The value of the sum is, like, that sum is just like first term plus second term. It's more discrete. So it stays this term for a whole unit. Then it goes to this term for a whole unit, then this term for a whole unit. So that should look like, oh, wait. Boom, boom. This is the value of the sum. That orange, I should have chosen two more different colors. Here's the purple. This is this purple area is the value of the sum. You see what I'm saying? It's like if I plug in 1 into my function, then that's the first term in the series. And then if I plug in 2 into the function, that's my second term of the series, et cetera, et cetera, et cetera. So what I'm saying is this purple left Riemann sum is the value of my series. So it's very clear to see that the purple is bigger than the red in that case. And then the other bound, maybe you want to think about it. Want to think about it, or you want to know the answer? Well, okay, let me tell you so I don't know what a good teacher would do. A good teacher maybe would let you think about it. But if I was a student in your seats, I would be like, no, come on, just let me know. So the other bound, for the upper bound, there's my function again. Again, the actual value of the integral is that red area. What this bound says is, now think of it as a right Riemann sum. Here's the value of the sum. Or sorry, here's the value of the first term. That's A1, the area of that rectangle. Here's the value of the second term. Here's the value of the third term. Now, if you think of it as a right Riemann sum, then you can see you take A1 plus this red area, that's going to be more than the value of this sum. And I guess that does a good job of giving you the intuition without, because that was so quick that maybe you didn't fully understand. So you take some time at home and see if you can convince yourself of that, but that's the intuition. All right. That's all I got. Did I give you your homeworks yet? Cool. Okay, then that's it. Tomorrow we'll do 10-3.